Hello, Mr. Hasty here. So this is going to be our last video of the year. It covers the first law of thermodynamics and the second law of thermodynamics and their applications. So the first law of thermodynamics says that the change to thermal energy, which we're going to call U, because that's what the book calls it, is equal to the heat added minus the work done. So as a formula, we can say that U, which is the thermal energy, is equal to Q minus W. Or sorry, delta U, the change in thermal energy. So what this means is that when heat is added to the system, potentially some of that can be transferred into work. And so as it's transferred into work, it doesn't add to the total thermal energy. So brief example is if you heat up a balloon, that balloon will expand. To expand, you're moving the balloon, which is very, very thin, but it is something that you're moving. And that means that you're doing work on that balloon membrane. And so the relationship between those two things is the total thermal energy. This is actually a restatement of the law of conservation of energy, which says that energy can't be created or destroyed. So if you're adding heat and some of that is being used to do work, then the total thermal energy is the difference between those that's added to the system. So, for instance, one thing that we know is true is that as you drop things through an environment, they actually collide with air particles and pick up temperature, they pick up heat, they pick up thermal energy. So how far would you have to drop a 2.00 kilogram brass ball to raise its temperature 2.0 degrees Celsius? So essentially what it's asking is, in this system, we have to assume that the amount of total energy is constant because energy can't be created or destroyed. So all the energy used, quote unquote, in dropping the ball will be picked up as thermal energy. So we have all the information to actually work out the amount of thermal energy, Q. Q is mc times delta T. Well, in this case, we know the mass is 2.00. We have to look up the specific heat of brass, which is 376 joules per kilogram Kelvin. And then we're raising the temperature 2 degrees, so that'd be a delta T of 2. So if we multiply those together, we get 1,504 joules. So that's the amount of heat if we assume all the heat was transferred to the ball of brass. Now the work done on the system, work is force times distance. So in this case, we have 2.00 times a distance that we don't know. Well, if all the work is transferred into thermal energy, which is what we're assuming here, because we don't have any other information to go on, we can just set that equal to each other. How does that make sense with our first law of thermodynamics? So we're saying that in this situation, there's no change in total thermal energy. We're saying that we have zero thermal energy equal to 1504 minus 2D. And we just solve for D in this case, and we will get 752, and that'd be meters. So you'd have to drop a brass ball 752 meters to raise its temperature 2 degrees Celsius. Now there are other factors in this. If we did a more realistic modeling, including drag and air coefficients, right? But if work is done on the system through gravity and it's transferred into heat this would be how it would be done. On a side note, this should have been restricted to 2 sig figs, so this should be 750 meters. Number 2, a drill is used to put a hole in a 1.55 kilogram piece of silver. How much work was done by the drill if the silver increases in temperature by 3.5 degrees Celsius? So let's talk about the Q, the heat. Well, we have a 1.55 kilogram piece of silver. We have to look up its specific heat, which is 235 joules per kilogram Kelvin. And then if we're increasing the temperature by 3.5 degrees Celsius, that's the same as increasing it by 3.5 degrees Kelvin. And when we multiply that, we get 1274.875. Now, it says how much work was done by the drill. And in this case, we're making a similar assumption. We're assuming that all the work done was transferred into heat of this piece of metal. Now, if you want a more realistic modeling scenario that involves some more complicated math, this is the basics of how it goes. So the heat was that many joules, which means that much work must have been done if it all transferred into heat. So we could say at least, rounding to appropriate sig figs, which seems to be 2, 1,300 joules. All right. Now, one of the things we use the first law of thermodynamics and the way we use it is something called a heat engine, which you guys learned about when you read about internal combustion engines. A heat engine has the job of turning thermal energy into kinetic energy. So the engine in your car does this. It turns the thermal energy from the explosion of gasoline and air into kinetic energy in the motion of your wheels. So now what you have there is you have an explosion. So what you really have is a transfer of chemical energy into thermal energy by the combustion process. The spark plug ignites the gas-air mixture and creates a lot of thermal energy. The thermal energy is then used to expand the gases, which then create the kinetic energy. So one of the things is that thermal energy in the form of heat creates what we call waste heat, because not all the thermal energy is going to be focused where we want it to be focused. So if we have a basic engine chamber, here's our piston. I'm very bad at drawing this. And we have an engine chamber. Well, the engine chamber is going to heat up on the sides. And that's not heat that's being used for the creation of kinetic energy. And because of that, we call that waste heat. Because of waste heat and the fact that you can't avoid it, even if your substance is a very good insulator, so that heat does not transfer to it, some heat will transfer. And that means that we have an efficiency problem. Not all of the thermal energy will convert into kinetic energy. And just like we talked about efficiency with simple machines, the amount of efficiency in a heat engine is relatively low in comparison. Even the most gas efficient cars are only about 40% efficient in converting the thermal energy into kinetic energy. And stuff like coal-fired plants and things like that provide electricity to your home that use thermal energy are only about 30% efficient, usually on the high end. So that idea comes down to the total thermal energy of a system, and how this relates to the first law of thermodynamics is equal to heat minus work done. So basically, we want the work to be done in the example of a heat engine. We want the work, but anything we lose to heat is going to take away from our total equation. Now, refrigerators and heat pumps are the exact opposite. So what refrigerators do is they cool things. We know that, but how do you do that? Well, you absorb thermal energy. And then you have to use mechanical energy to transport it. That's why they have a coolant system. A cool liquid goes through absorbs the heat, and then moves that heat away from where it's trying to cool. And then it removes it. A heat pump just does that in reverse. It heats up the liquid and brings it to where the heat can then dissipate out into the environment. So an example of a heat pump would be an old boiler furnace. You heat up the water, it moves through the house, and as it moves through the house, it radiates that heat off, goes back, repeat the cycle. Whereas a refrigerator sends the fluid through a cool place, usually using a coolant, a chemical coolant. It gets cooler. Then it goes by the main part of the fridge that needs to be kept cold. Because heat, and we're going to talk about this, because heat always goes to where it's cold, the heat tries to go into that coolant line. It absorbs some of the heat, and then it moves it out. Repeat the cycle, and you have essentially a way of mechanically moving. But to do it, you have to move that fluid. You have to do work on the system. So to do refrigeration or something like that, you have to apply work on the system. We all know what happens if your fridge goes out. Eventually, it starts to warm up. And the reason for that is the second law of thermodynamics. The second law of thermodynamics says that heat will spontaneously move. Spontaneously means without reason. From high concentration to low concentration. So, we know this intuitively if we think about it. If you put something that is really, 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 really hot in a box, like a cooler, it'll make the box really, really hot because it's trying to reach a set of equilibrium. I'll move from high concentration to low concentration. So the idea here is that we understand that if without any outside effort, your fridge is eventually going to equalize temperature with the outside environment. And when it does that, everything's the same temperature. And that's because of what we call the second law of thermodynamics. Now, that's based on something called entropy. Entropy is a measure of the dispersal of energy. So how much is the energy spread out? So let me give you a couple examples. Let's say we have a cooler, and inside that cooler we put one really, really, really cold chunk of ice, right? So there's a lot more thermal energy outside than there is inside the ice. This has low entropy. The thermal energy is very, very different from location to location. If you come back like months later, that cooler is not going to have kept that ice cool forever. It'll be liquid. Everything in there will be the same temperature. That system has a very high entropy. The energy is very dispersed throughout the system. So there is a formula that measures the change in entropy, which we call S. Delta S is equal to the amount of heat divided by the temperature. And the units there are joules per Kelvin. So entropy is kind of a weird concept. Another way to state the second law of thermodynamics is as time goes on, entropy will increase. And this is true of every system, including the universe. As time goes on, the energy gets less and less centralized. And this actually plays a big role in when we talk about the fundamentals of the energy debate. Basically, that over time on Earth, as Earth is a system, we will lose energy. Now, energy is being repurposed and transformed. We know it can't be created or destroyed, but as entropy increases, as the energy becomes more dispersed, it becomes harder to use. We like very concentrated forms of energy, like coal. Coal is a lot of chemical energy in one place. Nuclear power allows us to use the energy in the nucleus of an atom in one place. So that's easy to use. It's harder to use energy that's dispersed. So let's look at a quick example. How does the change in entropy differ for water going from 274 to 275 Kelvin versus going from 318 to 319 Kelvin? So let's calculate each of these. So when we talk about the change in temperature, right, we have to calculate the Q. In this case, going from 274 to 275, we're going to do mass. And let's assume we need to come up with a mass for this scenario. Let's say that the mass is 1 kilogram of water. So if we have 1 kilogram of water times the specific heat of water, 4,180, and we're going up by 1 degree Kelvin, that'd be times 1 again, and divided by the temperature, and that would be the starting temperature, so divided by 274. So the entropy there is, or the change in entropy at that particular transition from 274 to 275 is, with 3 sig figs, 15.3 joules per Kelvin. So we can think of that as every 1 degree change in Kelvin is yielding 15.3 joules difference of thermal energy in the form of heat. So what about the other scenario? Well, if we think about it, the top's going to stay the same. We have 1 kilogram of water, same specific heat. It hasn't gotten to vaporization point yet, so we don't have to worry about that. It's only going up by 1 degree, but our starting temperature is different. Our starting temperature is 318. Now, as you might imagine, because it goes up, the number on bottom goes up, our total amount of entropy is going to go down. So what that means is, as temperature goes up, the change in entropy goes down, and vice versa. As temperature goes down, the change in entropy goes up. So as you get closer and closer to absolute zero, right, as your temperature gets lower and lower, your entropy gets higher and higher, being up. So this actually leads us to a concept that as things get incredibly cold, the amount of dispersion, the amount of essentially flatness of energy in the system increases greatly. All right, guys, that's the last one. I will see you guys when we do the review for the upcoming quiz. Bye.